Okay, this will be a quick one. Hey, go check out the website and let me know what you think. There's some new tools on the front page that we are still working on. One of them, for example, is this CRISPR simulation lab. That needs more work, but basically you can place your target sequence define the gRNA and the edit sequence, and it will actually modify. It will have the original sequence as you have here and the edited one, where essentially I call the A's are replaced with T's in this case. And we have HG replaced with TA. Yeah, so editing your sequence. What else we got? Actually changed, so there's currently no ads. I mean, there's no overlay ads. So enjoy that. There are, however, ads within the text. What did we have? Yeah, optical illusions. Yeah, so the idea is, yeah, we want everything interesting to be shown on the, the first page, and then there will be ads within text. Yeah, this optical illusions actually generated using Python. And there's a Python code below every optical illusion example. Yeah, there's a bunch of them. This one actually, when you run the Python code, you can actually move this line left and right to actually see, well, because people don't believe that these two lines in a Ponzo illusion actually have the same length. So in this tool, you could use the slider to move it around and see that it's actually the same length. So I'm losing my voice. And yeah, so the ads will be in the text alone, hopefully. So I have to actually fix the placement. I have the knowledge graph generator, so you can read your papers this way. Yeah, so this is ideal where there's no ads on the first page when you load it. You can copy paste your text in here. It will generate a knowledge graph for you that you can move around and review. This will require more work. This one, so for example, the tool that we are working on at the moment, let's see what it looks like. Yeah. Okay, I have a lot of replication. Don't know why it works with some text but not the other. have to actually check what's going on. We change this to say ECG. What will happen? It made now a correlation between ECG and EEG. But yeah, we have ECG mentioned 17 times. How about fuzzy logic? Why fuzzy logic is not being mentioned? So there will be some sort of pre-processing that will be required. Yeah, I'm not sure about fuzzy. Fuzzy mentioned 18 times, so I don't know exactly what's going on. We'll have to check the code. I'll just pop the code at the bottom of the page as well for you to play around with yourself. But what we were doing yesterday, yeah, this fuzzy logic waveform detector. The idea for this was that you will be able to scroll through EEG signal. It will give you an artifact risk score. And currently, well, in theory, it should work if this first chart allowed us to actually scroll through the data. So we have to fix that. We have all the prompts, which, by the way, we are more than happy to place on the page. It's actually okay, let's see. So let's read this to see what the application is all about. And we will continue from there to development, or shall I say redevelopment.
Fuzzy logic algorithm for EEG data analysis. Overview of fuzzy logic. Fuzzy logic is a form of many-valued logic that deals with reasoning that is approximate rather than fixed and exact. In fuzzy logic, truth values can range between 0 and 1, representing the degree of truth. This approach is particularly useful for handling uncertain or imprecise information. Application to EEG data. 1. Defining signal characteristics. First, we define variables to represent different characteristics of the EEG signal, such as amplitude, frequency, noise level, and signal stability. Each characteristic is associated with a fuzzy set, which includes membership functions to represent different degrees of that characteristic, e.g., low, medium, high. 2. Membership functions. Membership functions are mathematical curves that define how each point in the input space is mapped to a membership value between 0 and 1. For example, an amplitude characteristic might have membership functions for low, medium, and high amplitude. These functions allow the algorithm to assess the degree to which a particular signal belongs to each category. MOS 3. Fuzzy rules. Fuzzy rules are if-then statements that describe the logic of the system. For EEG data, these rules might be structured as follows. If the amplitude is high and the frequency is low, then the signal quality is poor. If the noise level is low and the signal stability is high, then the signal quality is good. Each rule combines different characteristics and their degrees to infer the overall quality of the signal. 4. Fuzzy Inference System. The Fuzzy Inference System, FIS, processes the input data, EEG signal characteristics, through the fuzzy rules to generate an output. This involves fuzzification, converting the input values into degrees of membership; rule evaluation, applying the fuzzy rules to the fuzzified inputs to generate fuzzy outputs; aggregation, combining the fuzzy outputs from all rules; defuzzification, converting the aggregated fuzzy output back into a crisp value that represents the final assessment, such as the overall signal quality. 5. Implementation. Fuzzification. The EEG data is pre-processed to extract characteristics like amplitude and frequency. These characteristics are then fuzzified using the defined membership functions. Rule evaluation and aggregation. The fuzzified characteristics are input into the fuzzy rules. Each rule produces a fuzzy output, which is then aggregated to form a comprehensive assessment. Defuzzification. The aggregated fuzzy output is defuzzified to obtain a crisp value that represents the overall quality of the EEG signal. Benefits for EEG data analysis. Handling uncertainty. Fuzzy logic can effectively manage the inherent uncertainty and variability in EEG data. Flexibility. The system can be easily adjusted by modifying the membership functions and rules to accommodate different types of EEG data and analysis requirements. Interpretability. The rules and membership functions provide a transparent way to understand how the system evaluates the signal quality. In summary, the fuzzy logic algorithm enhances EEG data analysis by providing a structured yet flexible method for assessing signal quality based on multiple characteristics. It manages the uncertainty and imprecision typical of EEG data, ensuring robust and interpretable analysis outcomes.
Okay, so we have more prompts for it. This is just a general overview. So we are using Plotly for this. We need a folder and file structure. And let's quickly check this. This looks legit. Let's see what it will do. The thing about the general stuff is that we actually can create the Python code that will, well, do it all in-house, just Python alone. Should we do it or not? Wonder when we'll start developing. So just ask for more. So what the libraries it's going for? Let's make sure it's using SK fuzzy. Okay, what library are you going to use for the fuzzy logic analysis itself? Okay, it's actually going for it. It's going for it. So it's scikit fuzzy and SK fuzzy are different things, aren't they? Are scikit fuzzy and SK fuzzy same or different? Right, it's the same library. Okay, can you regenerate the file and folder structure again? Well, I said regenerate and then... Okay, it's the same one. Just update it quickly. No, it's literally the same. Okay, now it's going. Didn't ask for code, but it's going for it. Shall we let it continue? So we already have a my app. Yeah, can you use text alone to describe the code and how this application will look like in using text alone? Don't generate or include any code. Okay, can you just describe the application in general terms using continuous sentences and paragraphs?
This web application is designed to generate and analyze synthetic EEG data using fuzzy logic. The application is built with Flask, a lightweight web framework for Python, which serves as the backend. The backend code handles the generation of synthetic EEG data, processes the data, and performs fuzzy logic analysis to evaluate the quality of the signal. When a user accesses the web application, they are presented with a clean and intuitive interface. The main web page, served by Flask, displays a dynamic chart that visualizes the EEG data. This visualization is powered by a client-side JavaScript library that fetches data from the server and updates the chart in real time. The layout and appearance of the web page are styled using CSS to ensure a user-friendly experience. The application generates synthetic EEG data by simulating signal patterns, adding random noise, and incorporating periodic disturbances to mimic real EEG signals. This data is then processed using fuzzy logic, a method that deals with reasoning that is approximate rather than fixed and exact. Fuzzy logic is particularly useful for handling the inherent uncertainty and variability in EEG data. To analyze the EEG data, the application defines several characteristics of the signal, such as amplitude, frequency, and noise level. These characteristics are evaluated using fuzzy membership functions, which classify the data into different categories like low, medium, and high. Based on these classifications, the application uses a set of predefined fuzzy rules to infer the overall quality of the EEG signal. The results of the fuzzy logic analysis are then displayed on the web page. Users can interact with the application by scrolling through the EEG data and triggering the analysis process. The application dynamically updates the visualization and displays the signal quality assessment, providing users with immediate feedback on the data they are viewing. Overall, this web application combines robust back-end processing with an interactive front-end to deliver a comprehensive tool for generating and analyzing EEG data. The use of fuzzy logic allows for sophisticated data analysis that can handle the complexities of EEG signals, making this application a valuable resource for anyone interested in biomedical data processing.
The EMG beat. Okay, so the synthetic EEG generates synthetic EEG data with periodic EMG artifacts. Okay, we have three fuzzy variables are defined: amplitude, frequency, and artifact risk. Membership functions. Oops. Okay, I sent it by mistake. That's okay. Yeah, there's no EMG in the description.
Description of the application's functionality with specifics on fuzzy logic. This web application focuses on generating synthetic EEG data and analyzing it using fuzzy logic to assess signal quality, particularly focusing on the risk of artifacts. The core of the application is built using Flask, a lightweight web framework for Python which manages the backend processes. Backend functionality. Synthetic EEG data generation. The application includes a function, generate synthetic EEG, which creates synthetic EEG data. This function simulates realistic EEG signals by generating sine waves and adding random noise. Additionally, it incorporates periodic EMG electromyography artifacts to mimic real-world disturbances often seen in EEG data. These artifacts are introduced at regular intervals to simulate muscle movements or other sources of interference. Fuzzy logic analysis. To evaluate the synthetic EEG data, the application employs fuzzy logic. 3 fuzzy variables are defined for this purpose. 1. Amplitude represents the signal strength or the peak value of the EEG signal. 2. Frequency indicates the rate at which the signal oscillates. 3. Artifact risk assesses the likelihood of the presence of artifacts in the signal.
Okay, so in text alone, can you explain how the code should be updated? Okay, that looks legit.
Updating the code. Overview and steps. 1. Generating synthetic EEG data with periodic EMG artifacts. Function update. The generate synthetic EEG function should be updated to include the generation of synthetic EEG data with periodic EMG artifacts. This involves simulating a base EEG signal, typically using sine waves, adding random noise to the signal to mimic natural EEG variations, introducing periodic EMG artifacts at regular intervals to simulate muscle movement interference.
Okay, which part of the code meant to be regenerated and updated?
Parts of the code to be updated and regenerated. 1. Synthetic data generation function. Current focus. Enhance the generate synthetic EEG function to include periodic EMG artifacts. The function should simulate a base EEG signal, add random noise, and introduce periodic disturbances to mimic real-world EMG artifacts. Steps. Update the function to simulate a sine wave for the base EEG signal. Add a noise component to the signal. Introduce periodic high-amplitude, short-duration spikes to simulate EMG artifacts. 2. Defining fuzzy variables and membership functions. Current focus. Define the fuzzy variables amplitude, frequency, and artifact risk, and create trapezoidal membership functions for each variable. Steps. Create trapezoidal membership functions for amplitude to categorize it as low, medium, and high. Similarly, define trapezoidal membership functions for frequency, slow, moderate, fast, and artifact risk, low, moderate, high. This is 3. Implementing fuzzy rules. Current focus. Formulate fuzzy rules to infer signal quality based on the fuzzy variables. Steps. Create rules that combine the fuzzy variables to produce an assessment of signal quality. For instance, if amplitude is medium, frequency is moderate, and artifact risk is low, then signal quality is good. If amplitude is high, frequency is low, and artifact risk is high, then signal quality is poor. Add additional rules to cover other combinations of the fuzzy variables. 4. Fuzzy inference system and defuzzification. Current focus. Set up the fuzzy inference system to process the input values and generate a final signal quality assessment, then convert this fuzzy output into a crisp value using defuzzification. Steps. Implement the fuzzy inference system to evaluate the input values, amplitude, frequency, artifact risk, using the defined rules. Aggregate the outputs from all the rules to produce an overall fuzzy assessment. Apply defuzzification to convert the fuzzy result into a crisp signal quality value. 5. Updating front-end integration. current focus. Modify the front-end JavaScript and HTML to fetch the updated EEG data with periodic EMG artifacts, display it accurately, and interact with the new fuzzy logic analysis results. Steps. Update the JavaScript to fetch the synthetic EEG data with the enhanced characteristics. Adjust the charting logic to display the new data accurately. Ensure the interface displays the results of the fuzzy logic analysis, including the assessed signal quality and artifact risk. Handle user interactions, such as generating data and running analysis, ensuring smooth operation with the updated backend functionality. Hash summary of code parts to be updated. 1. Synthetic data generation. Enhance the generate.
Okay, and how's this web application interactive? Hey, can you provide a quick summary?
The web application is highly interactive, allowing users to engage with EEG data generation and analysis dynamically. It features a dynamic chart for real-time visualization of EEG signals, buttons for generating and analyzing data, and real-time feedback displaying signal quality and artifact risk. The front end uses AJAX requests to communicate with the back end, ensuring seamless data fetching and analysis without page reloads. Users can interact with the EEG signal by zooming, panning, and highlighting sections on the chart. The application is responsive, working well on various devices. This interactivity provides a smooth and engaging user experience for exploring and understanding EEG data.
Hey, can you explain again how the data will be generated or regenerated by the user? Can you always use continuous text, full sentences, whole paragraphs?
How the data will be generated by the user. When a user interacts with the web application, they will initiate the data generation process by clicking a button labeled Generate Data on the interface. This action sends an AJAX request from the front end to the back end, specifically to the Flask server handling the application. The backend receives this request and triggers the Generate Synthetic EEG function, which is responsible for creating synthetic EEG data with defined characteristics. The Generate Synthetic EEG function begins by simulating a base EEG signal using sine wave patterns. This simulation reflects the typical oscillatory nature of real EEG data. To add a layer of realism, random noise is incorporated into the signal, mimicking the natural variability found in actual EEG recordings. In addition to the base signal and noise, the function introduces periodic EMG artifacts. These artifacts are higher amplitude, short duration spikes that occur at regular intervals, representing muscle movements or other disturbances commonly seen in EEG data. Once the synthetic EEG data, including the base signal, noise, and EMG artifacts, is generated, it is sent back to the front end as a response to the AJAX request. The front end then updates the dynamic chart to display the new EEG signal in real time, providing immediate visual feedback to the user. After generating the synthetic data, the user has the option to analyze it by clicking another button labeled Analyze Data. This action sends the displayed EEG data from the front end to the back end through another AJAX request. The back end processes this data using fuzzy logic analysis functions. It evaluates the amplitude, frequency, and artifact risk of the signal, applying predefined fuzzy rules to infer the overall signal quality. The analysis results, including the assessed signal quality and artifact risk, are then sent back to the front end. Finally, the front end displays the analysis results next to the dynamic chart. This provides the user with insights into the quality of the generated EEG signal and the presence of artifacts, all in real time. This interactive process allows users to engage dynamically with the application, exploring and understanding EEG data effectively through a user-friendly interface. Debugging and fixing the code. The error you're encountering indicates that the fuzzy logic system cannot compute a crisp output because the total area for defuzzification is 0. This typically means that none of the rules are being activated based on the provided inputs. Here's a step-by-step guide to fix this issue. 1. Check input ranges. Ensure that the input values for amplitude, frequency, and artifact risk fall within the ranges defined by their respective membership functions. Resolving undefined signal quality output. The message signal quality undefined, check input values, indicates that the fuzzy logic system could not produce a valid output. This can happen if the input values do not activate any rules or if the input values are outside the expected ranges. Here are steps to further debug and resolve the issue. 1. Check input value calculation. Ensure that the calculations for amplitude val, frequency val, and artifact risk val are correct and debugging sparse fuzzy logic system. The error, crisp output cannot be calculated, likely because the system is too sparse, means that the provided input values do not activate any rules in the fuzzy logic system. Let's review and adjust the rules and membership functions to ensure the input values can trigger at least one rule. Steps to fix the issue. 1. Expand the membership functions. Ensure that the membership functions cover all possible ranges of the input values. 2. Add more fuzzy rules. Increase the number of fuzzy rules to cover a broader range of possible input combinations. 3. Adjust membership function ranges. Ensure that the input values fall within the range where membership functions are defined. Updated code app.py. Python from Flask, import Flask, render template, JSONify. Request import numpy as np, import skfuzzy as fuzz, import tyfuzzy.control as control, app equals Flask name, generate synthetic EEG data with periodic EMG artifacts. Def generate synthetic EEG, time equals further adjustments to ensure proper fuzzy logic evaluation. The issue persists, indicating that the current fuzzy rules and membership functions may still be too sparse. Let's address this by further expanding the rules and adjusting the membership functions to ensure that all possible input combinations activate at least one rule. Steps to fix the issue. 1. Expand the membership functions. Ensure the membership functions cover more ranges and overlap slightly to capture all input values.
Also, is what meant to happen every time I hit the analyze signal button? Should it be generating a new signal as well, or are we missing another generate signal button? Even with the current signal not changing, I get different results. Also, can we display everything necessary on the front page as well? Okay, can you give a summary for the code in text only?
The updated code for the EEG signal analysis web application introduces several improvements to enhance user experience and functionality. The backend, managed by Flask and app.py, now includes a global variable to store the current EEG data, ensuring that the analysis is performed on the same dataset until new data is generated. The function generate synthetic EEG simulates a realistic EE signal by combining a sine wave, random noise, and periodic EMG artifacts. The fuzzy logic system, defined using the scikit fuzzy library, involves three antecedents: amplitude, frequency, and artifact risk, each with their own trapezoidal membership functions covering low, medium, and high ranges. The consequent signal quality is similarly defined with membership functions for poor, average, and good quality. The fuzzy rules have been expanded to cover a broader range of input combinations, ensuring that at least one rule is activated by the input values. The analyze data endpoint computes the amplitude, frequency, and artifact risk from the current EEG data, ensures these values are within expected ranges, and then performs the fuzzy logic analysis to determine the signal quality. Debugging output helps verify that the input values are correctly calculated. On the front end, managed by main.js, there are now two distinct buttons: Generate Signal and Analyze Signal. The Generate Signal button fetches new EEG data from the server and plots it on a dynamic chart using chart.js. The Analyze Signal button sends a request to analyze the currently stored EEG data without generating new data, ensuring consistency in the results. The analysis results, including the signal quality, amplitude, frequency, and artifact risk values, are displayed on the web page. The HTML template, index.html, is designed to present the EEG signal, control buttons, and analysis results in a clear and user-friendly manner. The overall layout ensures that users can easily generate new EEG signals, analyze them, and view all relevant information in one place. These updates provide a more robust and interactive application for generating and analyzing synthetic EEG data using fuzzy logic.
Okay, so we're having a couple of problems. Okay, the code is great. Thank you very much. However, we would like to improve it further. First of all, when loading the page, can we make sure that the data is being loaded without the need to press the generate signal data? Also, currently we're getting the following error when pressing the generate signal button the second time. Can we make sure we address that? Also, can we make sure that when loading the page, the EEG signal is being shown, so the generate signal button is being automatically pressed for us, and also the analyze signal button is pressed, so we actually see the result. Also, it seems that sometimes we still getting the crisp output cannot be calculated error. So this is likely because the system is too sparse. Can we address this as well? So we have to check and make sure that the input values, whichever they are, always activate at least one connected term in the antecedent via the current set of rules. Could you also explain why does this happen and what the different terminology means? We have the explanation for it. Okay, so we auto generating the EEG data on page load, fixing the chat.js canvas reuse error. That should be straightforward. We automatically analyze the signal after it's generated and display the results. So that's all should happen when loading the page. And to ensure that the input values always activate at least one connected term, this error goes because the input values provided do not activate any rules in the fuzzy logic system. We have the, so essentially these values, which we actually want to display. So we'll be getting into it quite in depth shortly. Yeah, we're having an error. One of the functions might use the Copilot for it. Okay, so we're still getting errors, but it is working. Okay, we're still getting the crisp output. A cannot be calculated error. We need more details. Let's actually go back using ChatGPT. Yeah, we had that in the original code. A couple of things. First of all, we're getting this error that should be a simple fix, if you could just fix the necessary code without regenerating the whole thing, that would be good. Yeah, just go one by one. Just do one thing at a time. Stating the main.js is just the function, or currently we have 71 lines of code. Let's remain the same. Okay, now we're getting into the same era, vortex. Might need more details, is it? Oops. It's still getting the same error. Can you fix this for us? It's probably the order of things or something. We still have 71 lines of code. Right. Well, now it's working better. So every time it will give you a slightly different signal, which is great. It will analyze the signal. So we don't actually need the analyze signal button, do we? Give us a signal quality metric. It will look at the amplitude. Right, I'm still getting this undefined stuff. Okay, so we still seem to be getting the crisp output cannot be calculated error. We would like to dive deep into it. So, well, eventually we want to fix it, but we really want to understand why is this happening. If you could just provide text, full sentences, whole paragraphs, explanation, that would be great. Well, it's definitely better from what we had before. It's updating the code again. It's More rules? No, there are 12 rules already. What? Okay, we have to go over these rules.
Understanding the crisp output cannot be calculated error in fuzzy logic. The error, crisp output cannot be calculated, likely because the system is too sparse, occurs when the fuzzy logic system fails to produce a definitive result. This issue is typically rooted in the configuration of the fuzzy rules and membership functions within the fuzzy inference system. To understand why this happens, let's delve into the key components and mechanics of fuzzy logic systems. Fuzzy logic system components. 1. Antecedents, input variables. These are the input conditions or variables. Understanding the crisp output cannot be calculated error in fuzzy logic. The error, crisp output cannot be calculated, likely because the system is too sparse, occurs when the fuzzy logic system fails to produce a definitive result. This issue is typically rooted in the configuration of the fuzzy rules and membership functions within the fuzzy inference system. To understand why this happens, let's delve into the key components and mechanics of fuzzy logic systems. Fuzzy logic system components. 1. Antecedents, input variables. These are the input conditions or variables, such as amplitude, frequency, and artifact risk in our case. Each antecedent has membership functions that define how different ranges of input values map to linguistic terms like low, medium, and high. 2. Consequence, output variables. These are the outputs of the fuzzy logic system. In our case, the consequent is the signal quality, with linguistic terms like poor, average, and good. 3. Membership functions. These functions define the degree to which a particular input belongs to a fuzzy set. For instance, an amplitude value might partially belong to both medium and high sets, each with a certain degree of membership. 4. Fuzzy rules. These are the if-then statements that define the relationships between antecedents and consequence. A rule might look like, if amplitude is high and frequency is fast, then signal quality is poor. How the error occurs. The crisp output cannot be calculated error occurs when the input values do not activate any rules in the fuzzy logic system. This means that the input values fail to meet the conditions specified in any of the fuzzy rules, leading to a situation where the system cannot determine a definitive output. Several factors can contribute to this issue. 1. Sparse rule set. If the fuzzy rules do not cover the entire range of possible input values, there will be gaps where no rules apply. For example, if there are no rules to handle a combination of medium amplitude, moderate frequency, and moderate artifact risk, inputs in this range will not activate any rules. 2. Narrow membership functions. If the membership functions are too narrowly defined, many input values may fall outside the defined ranges, resulting in zero membership degrees for those inputs. For instance, if the high membership function for amplitude only covers values from 7 to 8, an input amplitude of 8.5 might not belong to any set. 3. Non-overlapping membership functions. Ideally, Membership functions should overlap to some extent, ensuring that every input value has at least partial membership in one or more sets. Non-overlapping functions can leave gaps where inputs are not covered by any set. Steps to address the issue. To resolve the error, we need to ensure that the input values activate at least one rule. This involves reviewing and adjusting the membership functions and rules. 1. Expand membership functions. Ensure that the membership functions cover the entire range of possible input values and have sufficient overlap. This will allow every input value to have at least some degree of membership in one or more sets. 2. Add more rules. Increase the number of fuzzy rules to cover all possible combinations of input values. This ensures that every combination of amplitude, frequency, and artifact risk activates at least one rule. 3. Review and adjust existing rules. Ensure that the existing rules are comprehensive and cover all plausible scenarios. Implementation adjustments. To address the error, we can expand the membership functions to ensure they cover the full range of possible input values with sufficient overlap. Additionally, we can add more fuzzy rules to cover a broader range of input combinations, ensuring that every set of input values activates at least one rule. This approach should mitigate the crisp output cannot be calculated error by ensuring comprehensive coverage of input scenarios in the fuzzy logic system.
In text alone, can you explain how can we visually review the existing rules? We would generally like to visualize as much as possible in the front panel.
Visualizing fuzzy logic rules and membership functions. Visualizing the existing fuzzy logic rules and membership functions can greatly aid in understanding how the system processes input values and why certain errors, like crisp output cannot be calculated, occur. Here's a step-by-step guide on how to visualize these components on the front panel of your web application. Steps to visualize membership functions. 1. Create graphs for membership functions. Display plots of the membership functions for each input variable, amplitude, frequency, and artifact risk, as well as for the output variable, signal quality. These graphs can show how input values are mapped to fuzzy sets like low, medium, and high. 2. Display fuzzy rules. Present a visual representation of the fuzzy rules. This can be done using tables or interactive charts that show which rules are activated based on the current input values. Visualizing membership functions. 1. Generate data for membership functions. For each input variable, generate data points that span the entire range of possible values. 2. Plot membership functions. Use a plotting library like Chart.js to create graphs that display the membership functions for each input variable and the output variable. Visualizing fuzzy rules. 1. Rule activation table. Create a table that lists all the fuzzy rules and highlights which rules are activated based on the current input values. 2. Interactive rule viewer. Develop an interactive viewer that allows users to see which rules are active by adjusting input values dynamically. Example implementation steps. Backend, Flask. 1. Generate membership function data. Create endpoints that generate data points for the membership functions of each variable. 2. Calculate rule activation. Create an endpoint that returns which rules are activated based on the current input values. Frontend, JavaScript and HTML. 1. Plot membership functions. Use chart.js to plot the membership functions on the web page. 2. Display rule activation. Create an interactive table or chart that shows the current state of rule activation. Detailed steps. Backend, Flask. 1. Generate membership function data. Create functions that generate data points for the membership functions. Create Flask endpoints to serve this data. 2. Calculate rule activation. Create a function that checks which rules are activated based on given input values. Create a Flask endpoint to return this information. Frontend, JavaScript and HTML. 1. Plot membership functions. Fetch the membership function data from the Flask endpoints. Use chart.js to plot these functions on the web page. 2. Display rule activation. Create an interactive table or chart that updates based on the current input values. Fetch the rule activation data from the Flask endpoint and update the display accordingly. Summary of implementation. 1. Generate membership function data. Backend functions to generate data points. Flask endpoints to serve this data. 2. Calculate rule activation. Backend functions to determine active rules. Flask endpoints to return rule activation data. 3. Front-end visualization. Use chart.js to plot membership functions. Create an interactive table chart for rule activation. This approach will allow you to visually review the existing fuzzy logic rules and membership functions directly on the front panel of your web application, making it easier to understand and debug the system. To effectively visualize the fuzzy logic rules and membership functions on the front panel of the web application, we need to enhance both the backend and front-end components of the application. This will involve generating membership function data, calculating rule activation, and displaying these visualizations dynamically. Backend enhancements, Flask. First, we need to create functions in the backend that generate data points for the membership functions of each input variable, amplitude, frequency, and artifact risk, as well as the output variable, signal quality. These functions will output the degree of membership for a range of input values, which will then be plotted on the front end. Additionally, we need a function that calculates which fuzzy rules are activated based on the current input values. This function will help identify which rules are contributing to the final output and highlight any gaps in the rule set that might lead to errors. To achieve this, we can create new Flask endpoints. One endpoint will serve the membership function data, and another will provide the current rule activation status. These endpoints will generate JSON data that the front end can easily consume and visualize. Front-end enhancements, JavaScript and HTML. On the front end, we need to integrate chart.js to plot the membership functions for each variable. This involves fetching the membership function data from the back end and using chart.js to create line charts that display how input values are mapped to fuzzy sets like low, medium, and high. These visualizations will help users understand how the input values are processed by the fuzzy logic system. Additionally, we need to create an interactive rule activation table or chart. This table will dynamically update to show which fuzzy rules are activated based on the current input values. By visualizing the active rules, users can see how different combinations of input values influence the final output and identify any scenarios where no rules are activated, leading to the crisp output cannot be calculated error. Implementation steps. 1. Generate membership function data. Implement backend functions to generate data points for membership functions. Create Flask endpoints to serve this data in JSON format. 2. Calculate rule activation. Develop a backend function to determine which rules are activated given a set of input values. Create a Flask endpoint to return the rule activation status. 3. Plot membership functions. On the front end, fetch the membership function data from the backend. Use chart.js to plot the membership functions for each variable, displaying the degree of membership for a range of input values. 4. Display rule activation. Develop an interactive table or chart on the front end that updates based on the current input values. Fetch the rule activation data from the backend and highlight the active rules in the table or chart. Example implementation outline. Backend, Flask. 1. Membership function data endpoint. Create a function to generate data points for the membership functions. Serve this data through a Flask endpoint. 2. Rule activation endpoint. Create a function to check which rules are activated based on the input values. Serve this data through a Flask endpoint. Front end, JavaScript and HTML. 1. Chart.js integration. Fetch membership function data from the backend. Plot the membership functions using chart.js. 2. Interactive rule activation table. Create an interactive element that updates based on the input values. Fetch rule activation data from the backend and update the display to show which rules are active. By implementing these enhancements, the web application will provide a comprehensive visualization of the fuzzy logic system. Users will be able to see how input values are mapped to fuzzy sets, understand which rules are activated, and identify any issues that could lead to errors in the fuzzy logic evaluation. This approach not only improves the transparency and usability of the application, but also facilitates debugging and optimization of the fuzzy logic system.
We also have another issue, well, minor thing at the moment is that because we have the generate signal button generating the signal and causing the analysis to be executed, do we really need the analyze signal button on the front page? Also, could you suggest ways to improve the EEG signal? So essentially, how can we make it look more realistic? We potentially would like to add controllers for the signal generation parameters on the front page as well, so we can see what difference does it make. Can we first get a response without any code using continuous text whole paragraphs?
Given that the Generate Signal button is currently responsible for both generating the EEG signal and triggering the analysis, the Analyze Signal button may no longer be necessary on the front page. Removing it can simplify the user interface, making the application more intuitive to use. Users would only need to press one button to generate and analyze the signal simultaneously, streamlining the workflow. To make the generated EEG signal appear more realistic, several improvements can be considered. First, the base sine wave used in the current implementation can be enhanced by incorporating multiple frequencies to better mimic the complex nature of real EEG signals. Real EEG signals are composed of various waveforms, including alpha, beta, delta, and theta waves, each with different frequencies and amplitudes. By combining these waveforms, the synthetic signal will have a more realistic appearance. Second, the noise component can be adjusted to better reflect the types of artifacts commonly found in EEG data. Instead of purely random noise, consider adding muscle artifacts, EMG, eye movement artifacts, EOG, and other physiological interferences. These artifacts can be modeled using different waveforms and patterns that are superimposed on the base signal. Third, introducing variability in the signal generation parameters can make the EEG data look more realistic. This includes varying the amplitude and frequency of the base waveforms, adjusting the intensity and type of artifacts, and incorporating non-stationarity to reflect the dynamic nature of EEG signals over time. To allow users to interactively adjust the signal generation parameters and observe the effects, adding control elements to the front page is a practical approach. These controllers can include sliders or input fields for parameters such as the frequencies and amplitudes of the different waveforms, the level of noise, and the intensity of specific artifacts. By adjusting these parameters, users can generate different EEG signals and immediately see the impact of their changes on the signal and its analysis results. In summary, the front page can be improved by removing the Analyze Signal button, enhancing the realism of the generated EEG signals through the incorporation of multiple waveforms and realistic artifacts, and adding interactive controllers for adjusting signal generation parameters. These changes will not only simplify the user interface, but also provide a more flexible and realistic simulation environment for users to explore different EEG signal characteristics. Sure, let's make this more concise and enjoyable to read. First, let's talk about simplifying the interface. Right now, you have two buttons, one to generate the EEG signal and another to analyze it. But since the Generate Signal button already does both tasks, why keep the Analyze Signal button? By removing it, you'll have a cleaner, more straightforward interface where users press one button to see everything they need. Now, about making the EEG signals look more realistic. Real EEG signals are a mix of various waveforms like alpha, beta, delta, and theta waves. Each of these has different frequencies and amplitudes. So instead of using just a simple sine wave, why not mix in a few different ones? This will make the synthetic EEG look much more like the real thing. Also, consider tweaking the noise. Right now, you have random noise, but real EEG signals have specific types of artifacts like muscle movements, EMG, eye movements, EOG, and other physiological interferences. Adding these will make the signal even more lifelike. Finally, how about giving users some control? Add sliders or input fields on the front page so they can play around with the parameters. Let them adjust things like the frequencies and amplitudes of the waveforms or the level of noise and artifact intensity. This way, they can see how these changes affect the signal in real time. In short, ditch the extra button, spice up the EEG signals with more realistic waveforms and noise, and let users have some fun tweaking the settings. This will make your application not only more user-friendly, but also more engaging and educational.
Yeah, I like the fun language with the complete sentences, continuous full paragraphs. That's great. I didn't update history.
Sure thing. Let's break it down in a fun and easy way. First off, let's simplify the interface. Right now, you've got two buttons, one to generate the EEG signal and another to analyze it. But here's the thing, the Generate Signal button already does both jobs. So why keep the Analyze Signal button around? Let's give it the boot. This way, your interface will be cleaner and more user-friendly. Users will only need to press one button to see everything they need. Easy peasy. Next, let's make those EEG signals look more realistic. Real EEG signals are like a complex symphony of different waveforms, alpha, beta, delta, and theta waves, each with its own unique frequency and amplitude. So instead of using just a plain old sine wave, why not mix in a few different ones? By combining these waveforms, your synthetic EEG signals will look much more like the real deal. It's like going from a simple tune to a full-blown orchestra. Now, let's talk about noise. Right now, your noise is just random, but real EEG signals have specific types of artifacts, like muscle movements, EMG, eye movements, EOG, and other physiological interferences. Adding these types of noise will make your signals even more lifelike. It's like adding those little imperfections that make something truly authentic. Finally, let's give users some control over the signal generation. Add some sliders or input fields on the front page so they can play around with the parameters. Let them adjust the frequencies and amplitudes of the waveforms or tweak the level of noise and artifact intensity. This way, they can see how these changes affect the signal in real time. It's like giving them the conductor's baton to direct the symphony themselves. So in a nutshell, let's get rid of the extra button, jazz up the EEG signals with more realistic waveforms and noise, and let users have fun tweaking the settings. This will make your application not only more user-friendly, but also more engaging and educational. Everyone loves a good symphony, especially when they get to be the conductor. Method, post, headers, content type, application JSON. Sure, let's dive into the updates with some fun and detailed explanations. Backend enhancements, making the magic happen. First up, the backend. We've supercharged the EEG signal generation process. Instead of just a simple sine wave, our new function combines multiple waveforms like alpha, beta, delta, and theta waves, giving you a symphony of frequencies and amplitudes that mimic real EEG signals. We've also added some realistic noise and artifacts to spice things up, simulating muscle movements and eye twitches. These artifacts make the synthetic EEG data look like the real deal. Plus, we've included parameters like noise level and artifact level so you can tweak these elements on the fly. To make this all work, we set up endpoints in Flask. When you hit the Generate Signal button, the backend gets your parameters, generates the data, and sends it back. Then, another endpoint analyzes this data, checking out the amplitude, frequency, and artifact risk before running it through our fuzzy logic system. This system has a bunch of rules that determine the quality of the signal, and we've expanded these rules to cover more scenarios. So, no more errors about the system being too sparse. Front-end enhancements. User-friendly and interactive. Now, onto the front end. We've streamlined the interface by ditching the Analyze Signal button. Who needs it when the Generate Signal button does both jobs? This means when you generate a signal, it's automatically analyzed and you get instant feedback. We've added some cool sliders for noise level and artifact level right on the front page. You can slide these around to see how different levels of noise and artifacts affect the EEG signal. This gives you a hands-on way to experiment with the signal parameters. To make everything visual and interactive, we integrated chart.js. This library helps us plot the EEG signals and showing you exactly what's happening. When you generate a signal, it gets plotted on a nice clean chart. We also display the results of the analysis, amplitude, frequency, and artifact risk, so you can see all the important details at a glance. Bringing it all together. When you load the page, everything kicks off automatically. The EEG signal is generated with your default parameters, and the analysis runs without you lifting a finger. If you want to change things up, just adjust the sliders and hit Generate Signal again to see how the new parameters affect the signal. The backend handles all the heavy lifting, while the front end keeps everything smooth and interactive. In summary, we've made the backend smarter and the front end more intuitive and fun. You get realistic EEG signals, instant analysis, and interactive controls to play with. It's a seamless experience that lets you explore the fascinating world of EEG signals right from your browser.
Okay, so it's generally working with no errors, which is great. However, the controls do not make much sense. See example images. Can you explain what's going on in text alone? Continuous sentences, whole paragraphs. Make it detailed but fun.
It's fantastic to hear that the application is running without errors. But I see there's a bit of a hiccup with the signal controls, and the generated signals aren't quite behaving as expected. Let's dive into what's happening. Signal generation and controls. Right now, the noise level and artifact level sliders are supposed to let you tweak how much noise and artifact intensity are added to your EEG signal. Ideally, moving these sliders should smoothly change the appearance of the signal, with higher values resulting in more pronounced noise and artifacts. But from the images you've shared, it looks like the generated signals are a bit chaotic and don't correlate well with the adjustments being made. What's going wrong? One, parameter sensitivity. The parameters might be too sensitive or not properly scaled. For example, a small change in the noise level or artifact level might be resulting in a disproportionately large change in the signal, making it look messy and unrealistic. 2. Signal composition. The combination of multiple waveforms, alpha, delta, theta, along with noise and artifacts, might not be balanced correctly. This imbalance can cause the signal to look cluttered or not representative of typical EEG data. 3. Noise and artifact characteristics. The way noise and artifacts are generated might be too uniform or too extreme. Realistic EEG noise and artifacts should vary and blend more naturally with the signal. How to improve it? 1. Adjust parameter scaling. We need to refine how the noise level and artifact level sliders influence the signal. This might involve using a nonlinear scaling function or limiting the range of these parameters to ensure more realistic adjustments. Number 2, balance waveforms. Ensure that the different waveforms, alpha, beta, delta, theta, are balanced and contribute to the overall signal in a realistic way. This might mean tweaking their frequencies and amplitudes so they complement each other rather than creating interference patterns that look unnatural. 3. Enhance noise and artifacts. Make the noise and artifacts more varied and realistic. Instead of adding a constant level of noise, use a function that simulates physiological variations. For artifacts, consider different types like eye blinks or muscle movements and vary their intensity and occurrence over time. Example adjustments. Imagine if adjusting the noise level slider added more subtle background noise rather than spikes. It would look more like gentle static rather than sharp peaks. Similarly, adjusting the artifact level app slider could introduce occasional but realistic artifacts that resemble real EEG disturbances, like periodic muscle twitches or eye blinks, rather than constant or uniform noise. The fun part. Think of your EEG signal like a beautiful piece of music. The different waveforms, alpha, beta, delta, theta, are like different instruments in an orchestra. They need to harmonize together to create a pleasant melody, a realistic EEG signal. The noise is like the ambient sound of the concert hall. It should be there, but not overpowering. The artifacts are like the occasional cough or shuffle in the audience. They should happen sporadically and naturally. Right now, it's like all the musicians are playing at random volumes and tempos, making the music sound chaotic. By fine tuning these elements, you'll turn that chaotic noise into a symphony of realistic EEG signals that respond naturally to your controls. This will make your application not only more accurate, but also more engaging and insightful for users exploring the fascinating world of EEG data. Sure, let's talk about how incorporating different waveforms like alpha, beta, delta, and theta as inputs can make your EEG signal generation more realistic and engaging. The magic of EEG waveforms. EEG signals are fascinating because they are composed of various waveforms, each representing different brain activities. These waveforms are like the different instruments in a symphony, each playing a unique role. By using alpha, beta, delta, and theta waves, you can create a rich and realistic EEG signal that captures the complexity of brain activity. Alpha waves, the calm background. Alpha waves are like the calm, soothing background music. They typically range from 8 to 12 hertz and are associated with relaxed, wakeful states, such as when you're daydreaming or meditating. Adding alpha waves to your EEG signal can create a steady rhythm that forms the foundation of your brain's activity. Beta waves. The active beats beta waves are the active, upbeat melodies. They range from 12 to 30 hertz and are linked to active thinking, problem solving, and focus. When you're engaged in a task or deep in concentration, beta waves dominate. Incorporating beta waves will add a layer of energy and alertness to your signal, reflecting moments of cognitive engagement. Delta waves, the deep bass. Delta waves are the deep, slow bass notes. They range from zero point 0.5 to 4 hertz and are most prominent during deep sleep and restorative processes. These waves are crucial for physical and mental rejuvenation. Adding delta waves to your signal will mimic those moments when the brain is in a deep, restful state, providing a slow and rhythmic undertone. Theta waves, the dreamy tunes. Theta waves are the dreamy, wandering tunes. They range from 4 to 8 hertz and are associated with light sleep, relaxation, and creativity. They often appear when you're drifting off to sleep or in a deeply relaxed state. Theta waves will bring a sense of creativity and tranquility to your EEG signal, adding another layer of complexity. Bringing it all together. By combining these waveforms, you create an EEG signal that's like a well-composed symphony. Each waveform plays its part, blending together to reflect the dynamic nature of brain activity. For instance, during a session of focused work, you might see a dominance of beta waves, with underlying alpha waves providing a steady rhythm. During relaxation, alpha and theta waves might dominate, creating a calming and serene pattern. Fun with controls. Imagine adding sliders for each waveform on your front page. Users could adjust the intensity of alpha, beta, delta, and theta waves and see how these changes affect the overall EEG signal. This would be like having a mixing board for your brain's symphony, allowing you to create different moods in the signal. For example, sliding up the beta waves could simulate an intense brainstorming session, while increasing delta waves could mimic deep sleep. By giving users control over these waveforms, you make the experience interactive and educational, letting them explore how different brain states might look in an EEG signal. Enhancing realism. To further enhance realism, ensure that these waveforms are blended naturally. Real brain activity is fluid and continuous, with different waveforms waxing and waning as the brain shifts states. Avoid abrupt changes, and instead use smooth transitions to reflect the organic nature of brain activity. The final symphony. In summary, by incorporating alpha, beta, delta, and theta waves into your EEG signal generation, you create a rich and realistic representation of brain activity. These waveforms, like instruments in a symphony, come together to produce a complex and engaging signal. With interactive controls, users can adjust each waveform, creating a personalized and educational experience. This approach not only makes your application more accurate, but also more fun and insightful for anyone exploring the world of EEG data.
Yeah, so we have something working. These are the default settings. You can't really see. Amplitude. Right, so that's the artifact. This is the noise. Yeah, we need the artifact level to be. Yeah, we need to adjust the levels. We have alpha. Let's check if the EEG makes any sense. Okay, so we have alpha, beta, delta, theta. And we can add noise on top of it. And the EMG artifact. It does make sense. Alpha free. So yeah, we need the values. Okay, let's ask the robot, and then it will become clearer as well, hopefully. Okay, so first of all, it's working with no errors. So this is great. Thank you very much.
You're welcome. I'm thrilled to hear that everything is working smoothly without any errors. It's fantastic to see the project come together successfully. If you have any more questions, need further adjustments, or want to add more features, feel free to ask. Happy exploring with your enhanced EEG signal analysis application.
This is what it looks like when we are loading the page. So everything seemed to work fine. I can move all the controllers. They seem to work okay. So that's great. They generate the signal quality, amplitude, frequency, artifact risk on the fly. So that's awesome. Just submit it as is, see what we get. The frequency. So if you take alpha frequency, the frequencies seem to work. I need probably a reminder of which one is which.
That's fantastic to hear. It looks like everything is functioning perfectly, and the interactive controls are working as intended. Your application now offers a comprehensive and engaging way to generate and analyze EEG signals with realistic waveforms and noise. What's next? Here are a few ideas to further enhance your application. 1. Visual enhancements. Color coding. Use different colors for each type of wave, alpha, beta, delta, theta, to visually distinguish their contributions in the combined EEG signal. Real-time updates. Show real-time updates of the signal as users adjust the sliders to provide immediate visual feedback. 2. Additional features. Save and load settings. Allow users to save their current settings, frequencies, amplitudes, noise level, artifact level, and load them later. Preset configurations. Offer preset configurations for common brain states like relaxed, high alpha, low beta, or focused, high beta, moderate alpha. 3. Educational tooltips. Tooltips and info boxes. Add tooltips or info boxes next to each slider explaining what the waveform represents and how it affects the EEG signal. 4. Data export. Export data. Allow users to export the generated EEG data and analysis results in a CSV or JSON format for further analysis or educational purposes. 5. User experience. Responsive design. Ensure the application is fully responsive and works well on various devices, including tablets and smartphones. Smooth transitions. Add smooth transitions and animations for slider adjustments to enhance the user experience. Celebrating success. You've created a powerful and interactive tool that not only generates realistic EEG signals, but also provides a hands-on way to explore how different brainwave components contribute to overall brain activity. This application can be a great educational resource for students, researchers, and enthusiasts interested in EEG analysis.
Yeah, that sounds great. Let's go one by one about what could be done next. Color coding sounds great. But I'm not sure how exactly are you gonna do it. Can you explain first? How are you suggesting to do the color coding? Now, real-time updates seem to be already happening. So that seems to be working okay already. So no changes needed there. Preset configurations sound good, but I suspect this might just complicate things too much. Let me know what you think. Tooltips and info boxes sound very good. So I could really use those, that they will really help. Also on the same topic, can we actually display the current value next to the sliders? Maybe. Unless you think it will be overpopulating the front panel. So I quickly also checked if how does it look on mobile, and it seemed to be good already. So that sounds promising. Yeah, if you can generate a response on all this using continuous text with whole paragraphs, and keep it technical but yet fun, that would be greatly appreciated.
Absolutely. Let's dive into each of these enhancements and see how we can make your EEG signal analysis tool even better, step by step. Color coding. Color coding the different waveforms can make it visually clearer which component contributes to the overall EEG signal. Here's how we can implement this. 1. Identify components. We'll separate the signal into its constituent waveforms, alpha, beta, delta, and theta. 2. Assign colors. Assign a distinct color to each waveform. For instance, alpha could be blue, beta could be red, delta could be green, and theta could be purple. 3. Plot components separately. Modify the plotting function to plot each waveform separately in its assigned color before combining them into the final EEG signal. 4. Combine and display. Overlay the colored waveforms on the same chart to show their combined effect. This way, users can see at a glance which frequencies are dominating the signal. It adds an extra layer of insight and makes the visualization much more engaging. Real-time updates. It's great to hear that real-time updates are working well. Since this feature is already in place and functioning correctly, no further changes are needed here. Real-time feedback is a fantastic feature that enhances interactivity and user engagement. Preset configurations. While preset configurations like relaxed or focused sound appealing, they might add unnecessary complexity to your current setup. Instead, focusing on user-driven customization with sliders allows for more exploration and learning. Presets could be revisited in the future if user feedback suggests a demand for them. Educational tooltips and info boxes. Tooltips and info boxes are a great addition to help users understand what each slider controls. Here's how we can implement them. 1. Tooltips. Use small pop-up boxes that appear when users hover over or click on the sliders. These tooltips will explain what each waveform represents and how it affects the EEG signal. 2. Info boxes. Place static info boxes near each slider with brief descriptions. For example, next to the alpha frequency slider, you could have an info box that says, alpha waves, 8 to 12 Hz, are associated with relaxation and calmness. 3. Current values. Display the current value next to each slider. This can be done using a small text box or label that updates as the slider is moved. This way, users can see the exact values they're setting, making the interface more informative without becoming cluttered. Mobile responsiveness. It's excellent news that your application already looks good on mobile devices. Ensuring a responsive design is crucial for accessibility and user experience across different devices. Since this is already functioning well, no changes are needed here. Putting it all together. Here's a detailed step-by-step plan for these enhancements. 1. Color coding implementation. Update the signal generation function to separate and color code each waveform. Modify the plotting function to display these waveforms in their respective colors. 2. Add educational tooltips and info boxes. Integrate tooltip libraries like tippy.js for hover or click-based tooltips. Add static info boxes next to each slider with brief descriptions of each waveform. Display the current value next to each slider, updating dynamically as the slider is moved. By implementing these enhancements, you'll make your EEG signal analysis tool even more interactive, educational, and user-friendly. It will allow users to visualize the contributions of different waveforms clearly and understand the effects of their adjustments through informative tooltips and value displays. This balanced approach ensures the interface remains clean and engaging without overwhelming the user. Let's get started with these updates and make your tool the best it can be. If you're ready, I can provide specific code examples for these enhancements.
Yeah, that sounds good. So we might try the color coding and see how we go. We don't want like too many things on the screen or too many colors. Because I think currently it's suggesting more a chart essentially displayed. So a chart for each EEG component in addition to the combined EEG. Now, so it's updating real time, so that's working okay. We're not changing anything there. Tooltips and info boxes. Yeah, if that works, we would like to add that, definitely, yes. So as much information as possible, but keeping the interface nice and clean. We have updated code to add color coding for each EEG component and integrate tooltips for each slider. So supposedly when I hover over, it will show me some useful information. That would be nice. Yeah, we like the interface informative and clean. Yeah, we don't want to overwhelm the user with too many elements. I think this probably already bordering too many elements. So we have updated JavaScript. Currently have already 100 lines of code, and we just added another 30 or so. Try it out. Can always, well, not always, but we should be able to revert back if something goes astray. Currently we have 60 lines of HTML. Okay, it has a what's called template, not template, what's placeholder. We don't like placeholders. Have to integrate. Okay, let's do the header. We do the body. Well, actually, yeah, we're adding spans to the body. Yeah, we might need to just generate the whole thing. Hey, can you actually generate the whole HTML code with all the necessary bit? So hopefully the JavaScript is complete. We're regenerating the HTML. Once the Python code is not the complete stuff, is it? It might be having trouble integrating. JavaScript now has the tooltips. Yeah, I can't see them actually, but assume that they're because they're actually working fine. Now in Python code, we can try it out. We have generate data. Yeah, it's a post. So what did we change? Yeah, we're returning way more data. It might not be ideal. Hey, let's comment that out for a sec. That instead. And now we also have a different generate synthetic data EEG function. Yeah, we only had EEG data before. Now we have the combined EEG data in each waveform separately as well. Yeah, I had a feeling this will be messy. This will be messy. Let's reduce the amplitudes for a sec. Just to make sure it's working okay. We could have less data points. Yeah. Um, where do we have the 1000? We have a time. Okay, can we just have 1 second? Kind of nice. I understand what we are trying to do, but it just looks so. And those are number of samples, not the time. Okay, let's try 2 seconds there. Yeah, the EG signal should be like overlay, be the primary thing, and everything else should be in the background kind of thing. Yeah. Yeah, this is actually kind of taking different direction. We might split this into two separate tools actually. One that shows the EEG generation, and the other one should just do the fuzzy logic business, because it's a whole separate story. Because we currently have an EEG generator, but it's old and it needs more love. Doesn't actually change. Yeah, we could update this one. This one is up and running. You can use it already. We'll be leaving it as is, and we'll be having another a more advanced options, or one that has different features. One doesn't have selection for noise, which is unfortunate because like the noise is there, so it could have been added fairly easily. Yeah, the frequency could really be fixed. Yeah, we could have the amplitudes on the left, frequencies on the right. Yeah, the original idea. So that was an EMG artifact thing. Yeah, the problem with the amplitude should be normalized. Yeah, I should be able to see that the EMG, so there's a EMG in the beginning. Should be able to see it. And there would be another one if the signal was long enough. The other question is this application might be, as it is at the moment, might be overloading the server. There might be too much happening there. Okay, first we have that error in the browser, some reference error. And then undefined plugin. We'll have to fix that. It's actually only happening on page load, but then everything is still working fine. Now the other thing is, as you can tell from the image, there is too much going on in the chart. We do not like that. It will be generating for a while. We might continue this tomorrow. Yeah, take a look at bionichaos.com. Let me know what you think. I'll be reviewing your feedback and addressing any issues during the next live stream. Thank you for your input. We really appreciate your time. I'll see you next time. Bye.